In this video, we're going to use what we've learned about sums of squares to revisit some more familiar statistics. So in your first class, you probably learned about r squared, also called the coefficient of determination. And r squared tells us the proportion of the total variation in the response variable that's explained by the sources specified in the model. So in your intro stat, I'm guessing you probably saw this in the context of regression, looking to see how far the points fall from the line on a scatter plot, but it can actually be used more generally than that. So we can use it here where we're just comparing groups. So r squared is the proportion of the variability that's explained. So obviously we're going to put the sum of squares total on the bottom. And then on the top, if we want to see the proportion that's explained, we're going to use sum of squares groups. Remember, sum of squares groups is one way to describe the amount of variability that is explained in the data. Another way that you could say it is 1 minus the unexplained variability. So you could do 1 minus SS error, which is unexplained, again out of the total. And if I want to calculate these values in JUMP, I need to get what's called an analysis of variance table. So I'm going to start off the same way we've done before for a t-test. I'm going to do analyze fit y by x. And again, I'm putting my response in the y box and my explanatory in the x box. And I'll click OK. So before, at this point, we've been doing a t-test. Right now we're going to do the means and ANOVA option. And there's a lot of different output that's given here, but I want to focus on just this little bit, the analysis of variance, where it tells us the sums of squares. And I can see when I look at these values that if I add up my sum of squares for groups and my sum of squares for error, that gives me the sum of squares for total. Sometimes we say we have decomposed the variation or just broken up the variation into its parts. So we had our sum of squares total, and we broke that up into the sum of squares for groups, which is the explained variation, plus the sum of squares for error, which is the unexplained. Okay, so I'm going to use this ANOVA table to calculate my r squared, and it doesn't matter which of these formulas you use, so I'm just going to do SS groups 7.56, let's keep 3 decimal places, 3, divided by the total, which would be 109.213. And we get 0.069. So if I want that as a percent, I would say 6.9. And I'm going to interpret this in context. So 6.9% of the variation in ratings, so the ratings of how effective people think the drug is, 6.9% of the variation in ratings is explained by this model. So the model that's based on whether it was text and graph or text only. And it's not too surprising that the r squared value was low there. We saw that our group means really weren't all that far apart. They weren't that far from the overall mean, and there was a whole lot of overlap in this distribution. So the amount of variability explained is sort of low. We can also use the concepts of variability between groups and variability within groups as we think about the t-statistic. So if we look at the numerator of the t-statistic, the mean for group 1 minus the mean for group 2, this is basically just describing the variation between the groups. Right? How far are the group means from each other? So this is kind of like SSG. The group standard deviations, these are describing the variation within the groups. Right? This is telling us how spread out the individuals are within each of those groups. And then there's one other thing here that doesn't show up in the r squared, which is the sample size. So r squared is really a way to look at the strength of the association. How far apart are the groups? How much overlap is there? Whereas the t-statistic is a way to measure the strength of evidence. So in addition to the strength of association, which it does have here between groups and within groups, it's also taking into account the sample size. So the larger your sample size gets, the larger your t-statistic gets, because that's providing stronger evidence.